too far along here. So Redstone check, fact or fiction. Under the Redstone check, when it's used to determine the uncertainty of a calibration system, the basic premise is that to determine total system uncertainty, all that you really need to do is this function called the Redstone check and add to it your reference uncertainty, and that'll give you your system uncertainty. Now, I guess the first place we should start is by asking, what is the Redstone check and what does it do? This is what the Redstone check has been documented to do. It includes all errors due to electrical and mechanical noise, distortion, cross-axis motion, basically all the factors that we need to consider when we're coming up with the uncertainty of a system. The Redstone check supposedly measures and determines all of them except for the uncertainty from the reference sensor. The method for the Redstone check is described down here below. We use a known transducer, or a reference standard, to calibrate a second sensor, a test sensor, which is called ref B. We then make ref B our reference for the system. We use it to calibrate ref A. We then compute the difference between the value we just determined for ref A and the original data provided by whoever's doing the calibration on the standard, and this gives us the uncertainty of the system. So this is kind of how it's been used, and you can see it here on a spec sheet in action. We have this STU, System Transfer Uncertainty, which is the portion determined by the Redstone check. We have the uncertainty of the reference sensor, and then we combine those to get the expanded system uncertainty, or ESU. Here are some of the values that come up. So today we're going to play scientist. We have this documented method for determining uncertainty. It has a claim of doing a good job. And now we're going to take that data and we're going to validate it on our own system and see what happens if we were to perform the Redstone check on the 9155 system using a flexure shaker. So, switch gears here real quick. So what I have set up today is I have a flexure shaker, the same one that we used in the last presentation. I have my test sensor mounted on top of my reference. So this guy is ref A. The little guy on top is ref B. For the sake of time savings, I've already done the first portion of the calibration. I have used ref A to calibrate ref B. And here are the calibration results. You can see a little bit of bumpiness in here, but let's just see what happens. So next part of the process, according to the Redstone check, is I use ref B as the known transducer to calibrate ref A. So go to my software and I'm going to change my reference sensor to this one. I'm going to change my test sensor to the one below. I'm going to reverse the cables on the system, which I've already done. And now I'm going to run a frequency response test on the reference sensor. Of course, we're zipping through the points of the calibration as usual. At the low frequency, we can see the shaker move, of course. Okay, and as we approach the end here, we can see some distortion on the waveform. And now we've completed our calibration. So I'm going to export the data from this so I can do a comparison. Move to my desktop. I did a little bit of preparation ahead of time, of course. This spreadsheet contains the original data, the 301A10 we just calibrated. Bring in my new sensitivity values. This is the difference between our old value and our new value, which is the result of the Redstone check. As we can see, the results look very good. 0.29% here being the highest point. This is the uncertainty of the reference sensor. So under the Redstone check, the total system uncertainty of this calibration system are these values right here. So right now I'm feeling good. I have my values, they look good. I'm really excited about my calibration system. So what do we do next? It's a requirement for accreditation. We do an interlaboratory comparison. So we're going to move over to this tab right here. For our interlaboratory comparison, we're going to choose to use this teardrop accelerometer, and we're going to send it to PCB. Now, of course, we're not going to wait for PCB to do the results. Instead, we're going to look at the previous PCB results. Same thing. We're going to, those are right here, copy those into this spreadsheet. And uh-oh, what's this? We have failed our interlaboratory comparison. This does not look good. We have failed our accreditation. Our customers are unhappy, and we don't know what's going to happen. So let me explain what happened. The reason the Redstone check does not work is we perform two calibrations. This is the equation that we're running when we run the calibration. When we calibrate the sensor during part 1 of the test, our transverse error appears up here. Note that this error is present when we're doing real calibrations as well. We calibrated the sensor. This is how it's getting compared to PCB. During the second step of the test, we made the 352C22 our test sensor, so the transverse error appears down here. And it's the same error, roughly the same amount. The end result, when we do the calculation of under the Redstone check, is the two errors cancel each other out. Now, when we're evaluating uncertainty, we cannot cancel out errors. We have to accommodate all of the errors. So this is where the Redstone check truly fails. Any systemic error in the system that occurs during the first part of the test and the second part of the test cancels out. Now, transverse motion is the error that we demonstrated disappearing under the Redstone check, but there's actually a number of other factors that are also not captured. Shaker distortion is something that the Redstone check is going to ignore. Transverse motion we saw, base strain, relative motion, and thermal drift of the sensors over an extended period of time are all not going to be captured by the Redstone check. So this leads us to the conclusion that we cannot use the Redstone check to calculate system uncertainty.